Ever looked up at the night sky and wondered about its true shape? I mean, the whole thing, not just the Earth or the Sun, or even our Milky Way galaxy. I'm talking about the entire universe. Does it go on forever in a straight line? Does it curve back on itself like a giant cosmic ball? Or could it be something even weirder? Think about it. When you're inside a room, you can usually tell its shape. But what if the room was so enormous, so mind-bogglingly vast, that you couldn't see any edges? So how do we even start to think about the shape of something that might be infinite? We use mathematics, the language of the cosmos. We use observations, peering deep into space and far back in time. The shape of the universe is deeply connected to its past, its present, and its ultimate fate. So, buckle up. We're going on a journey to explore the possible shapes of our cosmic home. When cosmologists talk about the shape of the universe, they often start with three main possibilities. These shapes come from Albert Einstein's theory of general relativity. It tells us that matter and energy warp space-time. The first, and perhaps simplest to imagine, is a flat universe. Think of a perfectly flat, infinite sheet of paper. In this kind of universe, if you send out two parallel beams of light, they stay parallel forever. The second possibility is a closed universe. Imagine the surface of a sphere. It's finite, but it has no edge. If you travel in a straight line on a sphere, you eventually end up back where you started. In a closed universe, space curves back on itself. Those two parallel beams of light we talked about, in a closed universe they would eventually converge. Then there's the open universe. This one is a bit like a saddle or maybe a Pringle chip. In an open universe, space curves outwards. If you send out two parallel beams of light, they would diverge. An open universe, like a flat one, is infinite in extent. So, flat, closed, or open, these are the big three contenders based on how space itself can bend. Each of these shapes has profound implications. A flat or open universe will likely expand forever. A closed universe, on the other hand, might one day stop expanding and start to collapse. Scientists measure something called the density parameter, omega. If omega is exactly 1, the universe is flat. If omega is greater than 1, it's closed. If omega is less than 1, it's open. So, how do we actually measure the shape of the entire universe? We look for the oldest light in the cosmos, the cosmic microwave background, or CMB. This is the afterglow of the Big Bang, a faint radiation that fills all of space. Tiny temperature fluctuations in this ancient light hold the key. Two incredible space missions, NASA's Wilkinson Microwave Anisotropy Probe, WMAP, and the European Space Agency's Planck satellite, have given us our best views of this CMB. They mapped these tiny temperature differences with incredible precision. By studying the characteristic size of the hot and cold spots in the CMB, scientists can work out if space is flat, curved positively like a sphere, or curved negatively like a saddle. And what did these amazing satellites find? The data from both WMAP and Planck strongly suggest that our universe is remarkably, astonishingly flat. This finding was a huge deal. It confirmed a key prediction of the theory of cosmic inflation. This flatness has big implications for the total amount of stuff, matter, and energy in the universe. The flatness points to a very specific cosmic recipe. While a flat geometry is what the big observations point to, flat can still allow for some pretty interesting overall shapes or topologies. Think about a flat sheet of paper again. You can roll it into a cylinder. The surface is still flat locally. Draw a triangle and its angles add up to 180 degrees. But globally, it's different. If you walk off one edge, you reappear on the opposite side. Now take that cylinder and connect its ends. You get a torus, a donut shape. A three-dimensional torus universe would be finite, but if you traveled far enough in any direction, you'd end up back where you started. Scientists have searched for such repeating patterns in the cosmic microwave background and in the distribution of galaxies, but so far, there's no definitive evidence for a torus shape on the scale of our observable universe. It seems if our universe is a donut, it's a very, very big one. These exotic topologies could still be perfectly consistent with the observed flatness of the universe on large scales. The search for these more complex shapes continues. So we've talked about flat planes, spheres, saddles, and even cosmic donuts. But why does any of this matter? Why do scientists spend so much time and resources trying to figure out the shape of the universe? Well, for one, it's about understanding our place in the cosmos. Are we living in an infinite expanse, or a finite, wrapped-up reality? Knowing the shape helps us understand the fundamental nature of space itself. Beyond satisfying our cosmic curiosity, the shape of the universe is intimately linked to its ultimate fate. A closed universe with positive curvature would likely collapse in a big crunch. A flat or open universe with zero or negative curvature would likely expand forever, leading to a big freeze or even a big rip. The fact that the universe is so close to flat is a major piece of evidence supporting inflation. Future observations, perhaps with even more precise cosmic microwave background telescopes or vast galaxy surveys, might give us more clues. For now, we live in a wonderfully mysterious cosmos, one that continues to surprise and inspire us. Keep looking up, keep wondering, because the universe still has plenty of secrets to share.